Thank you. My name's Scott O'Daniel. I work for the Umatilla Tribe's GIS program. Today I'm going to give a talk entitled Future Flows for the Upper Umatilla River. The work for this talk has been done by myself and my colleague and co-author on this project, Bethy Rogers-Pacheco. Today I'll be presenting some of the results from a hydrologic modeling exercise that incorporates changing precipitation, air temperatures, and atmospheric carbon to forecast stream flow into the late 21st century for the Upper Umatilla River. This talk will highlight some of the model outputs and the types of changes in the future stream flows that we anticipate. These two slides show the annual average precipitation, both rain and snow. To orient ourselves, the state line is shown in the middle in a thick black line, and the Columbia River follows part of that line up to the Oregon-Washington border. The Umatilla and Walla Walla rivers are clearly shown. This legend applies to both maps. On the right side is the annual average precipitation from 1971 through the year 2000. I meant on the left side, the legend shows precipitation from annual averages from 1971 through 2000. On the right side of the map is the predicted precipitation from near the end of the century. There's a little more precipitation that's shown in the future map. While the annual average precipitation is likely to increase in the future, much of it will fall in the form of rain rather than snow. Again, these two maps show the same area, but display something called the snow water equivalent, or another word for snowpack if it were melted down into water. These measurements are taken or predicted on January 1st on the left, and again on the right is the future forecast. January 1st is important because it is historically part of the snowiest portion of the year. The goal of this project is to take information like this and use it to make predictions about flow in the Umatilla River. Before we can do that, though, we need to understand the physical attributes of the Umatilla River watershed, things like land cover, slope, and soil. It's also worth noting that the snow water equivalent on the left, the historic range, is dramatically lower in the future, shown on the right. So back to understanding the watershed and some of the land cover, slopes, and soils that dominate hydrologic flow through the basin. We used a standard USGS cover map of the Umatilla River watershed. Remember, we're modeling the upper part, or above Pendleton, on the Umatilla Reservation and on the National Forest Service land. This land cover pattern reflects a precipitation gradient of rainfall, moving from drier areas in the western portion of the basin, about 7 inches of annual precipitation near Hermiston, to relatively high precipitation in the highest parts of the basin, over 40 inches of annual precipitation. We'll show modeled stream flow at 2 USGS gauges along the Umatilla River that collect water from different areas and show different combination and characteristics of land cover, soils, and slope. Here we show some of those combinations of land cover, soil, and slope. The image in the upper left corner is our study area, the colored part. In order to realistically simulate the movement of water through the landscape into the river, we divided the Upper Umatilla River watershed into 36 sub-basins shown in the gray images below. Next, we combined attributes of the soil water holding capacity, the slope, and the land cover to model the movement of water through the landscape and into the main stem river. Examples of each of these sub-basins and the soil, water, slope, and land cover characteristics are described in these smaller maps. we used two gauges with historic data to compare the changes at the flow at Gibbon, shown here in the upper Umatilla Basin, and at the West Reservation boundary, shown to the west. The east-west orientation of the basin is very important because large winter storms, sometimes known as atmospheric rivers, move in from the Pacific, often up the Columbia Gorge and into the Umatilla, as shown by this animation. This basin orientation affects the hydrologic response of flooding because the storm saturates the lower basin first. So when runoff from the upper basin arrives in the middle and lower floodplains, they're already full of water. These effects can be detected by analyzing the hydrologic record of the gauges along the river. Some example flows from the Umatilla River are shown here. The top image shows a flood on April 9th, 2019, where the Umatilla River at the Mission Bridge carried approximately 3,500 cubic feet per second of water. The lower image, taken on November 5th of 2019, shows near double that volume. So in order to try to communicate the model outputs, we compare the 88-year record at each gauge, in this case Gibbon, and the distribution of monthly average flows across the year. The highest March flow that was ever recorded is the very top bar, the dark blue bar with the value 37. That was in 2019. The dot in the middle of each of the bars represent the average, and the median blue bars show the range from the highest among the flows each month. As you can see, there's great variability within each monthly average. The difference between a wet year and a dry year can sometimes be up to 10-fold. Historically, the wettest months have been in the spring, when winter snow melts. Here we show a graph for the West Reservation boundary that shows similar information. The average monthly flows at the West Reservation boundary gauge are shown over a 26-year record. The distribution of flows looks similar to Gibbon, but with increased flow volumes that represent more water flowing into the catchment downstream. Monthly variability is also quite high. Again, up to a 10-fold difference in the range, for example, April, and the annual peak is still centered in the spring, in April. Again, the dark blue bar at the top of April shows that in 2019, April flows were the highest that were ever recorded for the month. These next two slides will compare some of the historic data and the modeled data. The modeled data will show our predictions in 2080 from outputs at Gibbon and the West Reservation boundary. The blue bars show the same data that you saw on the previous historic slides, and the red or pink bars show the modeled flows from 80 model runs based on a high emission climate change scenario in 2080. Note that the vertical axis or the range of data has increased. Modeled winter flows show a large increase from the historic range. These models suggest that by the end of the century, a wet month could far surpass the spring floods anytime between November and May. Even the average March or April flow could exceed the historic record. Additionally, the variability increases on the low side as well. Many of the examples of this are in January, February, and March. If you remember back, this is mostly because rain represents the precipitation falling in winter rather than snow that would have fallen historically. Again, the gauge at the West Reservation boundary shows a similar pattern. Wet months could be much wetter than the historic record. Dry months could also be much drier than historic averages. With the exceptions of January, February, and March, which aren't predicted to be as dry as the historic data, again, because precipitation is falling as rain rather than snow. And so the precipitation has no lag as it contributes to the river. The magnitude of these results were unexpected, and we sought out other models to compare with ours. This graph shows results from a University of Washington study for tributaries of the Columbia River. This is the Umatilla River at Pendleton. The pattern of these results are very similar to ours, including high monthly variability. The University of Washington used different methods and different data sources than we did. The units on the y-axis are different for these last slides. They used the depth of water across the entire watershed to represent flow, but the patterns are very similar. High winter variability is found in both the Umatilla on the left, the Walla Walla in the middle, and the John Day on the right. These results led us to believe a big part of the story is the natural variability of weather patterns and the responsiveness of rivers to individual storms. You'll remember the high-tech animation earlier and the storm path in the Umatilla that crosses from west to east. Our initial conclusions from this work is that increased flow variability is predicted for the upper Umatilla River. The form of precipitation changes from snow to rain, and the Umatilla River will likely receive higher winter flows. Regional scale climate patterns will likely increase the frequency and the intensity of these flows toward the end of the century. Additionally, patterns of predicted stream flow for the upper Umatilla are consistent with regional forecasts, like those from the University of Washington. These results have implications for native fish and aquatic animals that will be widespread. And it's important to remember that these floodplains where the rivers, the landscapes of the rivers are their own landscapes and should be managed as such. Floodplains are largely self-maintaining, and there's ecosystems on the planet. There is initial guidance for this kind of management in many documents, including the Umatilla River Vision, Floodplains by Design, and other guidance from the Association of State Floodplain Managers. It's also important to remember that salmon have withstood many harsh conditions over the last 10,000 years. They've reestablished in many unhospitable environments like the Toutle River after the Mount St. Helens eruption. And if our modeling is correct, we anticipate that the life history of Chinook will be the most impacted from future changing flows. Thank you very much.
That was great. Let's see, I will stop recording.